Hi everybody, this is Mr. Bowman, and in this section we are going to talk about numerical limits and non-existence of limits. Really what we're going to focus on is how do you find a limit algebraically and then find a numerical result for that. So we're going to start out with a Desmos demonstration, and here is an example. I want to find the derivative, the slope of the tangent line at the point 2, 3. So what we're going to do is we're going to think of another point on the function, and this one is some arbitrary location, the green point that you see there. And we are going to think about drawing the secant line between those 2 points and then moving the green point towards the point where we want to find the derivative, and you will see the slope of the secant line approaches the slope of the tangent line, and as that green point gets infinitely close to the blue point, we get a tangent line, and then we will have our slope. So what we're getting at here is we're getting at limits as the x value, the green x value, approaches the blue x value. So let's change gears here and take a look at this same function on a graph here. And what we're going to do is we're going to call that second point on the graph x comma f of x. We're just going to make it some generic value or point. So here's what we're going to do to find the slope of the tangent line at the point 2, 3. We're going to pick this arbitrary point. We're going to call it x f of x, and we're going to draw as best we can a secant line through both of those points. And what we're going to do is we're going to move the point x f of x closer to the point 2, 3, and we're going to do that using a limit. So f prime of 2, so the slope of the tangent line to that function f at 2 is equal to, we're going to find the slope of the secant line, f of x minus f of 2, so the change in y, over the change in x, x minus 2, as the limit as x approaches 2. Okay, so we're going to evaluate this algebraically. The limit as x approaches 2 of f of x, well, f of x is known to be x squared minus 3x plus 5 minus f of 2. So we are literally plugging 2 into the function. So 2 squared minus 3 times 2 plus 5, that's f of 2 over x minus 2. Now, you might want to try and plug in 2 right away, but you will see that if you do, you get 0 in the denominator. That's not going to work. That is often the case. So the limit as x approaches 2, we're going to simplify the numerator, x squared minus 3x plus 5 minus, if we simplify that whole thing up there in parentheses, it's going to be 3, and you can verify that, over x minus 2. Again, still can't plug 2 in because it'll make the denominator 0. So the limit as x approaches 2 of x squared minus 3x plus 2 over x minus 2. Still can't do anything with that. However, if you notice, you can factor the numerator. So the limit as x approaches 2, the numerator factors into x minus 1, x minus 2, all over x minus 2, and you saw some of these in the last chapter. We can always cancel out what we can factor out of the numerator and denominator, so this becomes the limit as x approaches 2 of x minus 1. Now, if we substitute in 2, we get 2 minus 1, which is 1. So what we're saying is that this line that I'm about to draw here in red, the tangent line, has a slope of 1. And that's one method of finding the derivative at a point. And it requires a little bit of algebra, nothing too terribly difficult, that you are going to have to know how to do. So there are some cases where derivatives do not exist at a point, and I would like to go through those right now. One of them is where the tangent line is vertical at a point. If that's the case, then you would have no slope, as you remember from geometry, in which case you don't have a derivative. From back in the previous chapter, when we talked about limits, the left and the right limits have to be equal. So if you have a sharp corner like you do in the middle figure, 2.32, the slope from the left is going to be like that, and the slope from the right is going to be like that, and those are not going to be equal to each other. So you don't have a derivative at a corner either. And then finally, if you have a discontinuity, you do not have a derivative, and that's for the same reason as the previous example, because the slope from the right is going to be like that, and the slope from the left is going to be like that, and they're not going to be equal. So the limit does not exist, and therefore the derivative does not exist. So this next page talks about points where derivatives do not exist, and I'd like to highlight a few things. If a function is not continuous or has a sharp corner at a point, the rate of change does not exist at that point. The rate of change, the derivative, aka the derivative. If a continuous function has a point where the tangent line at P is vertical, the rate of change does not exist at that point. So again, there's no slope. Therefore, which is what those three dots mean, no derivative. And that's summarizing the examples we just talked about. So now we want to talk about a differentiable function. A function is differentiable. You can find its derivative at a point if the instantaneous rate of change, the derivative, that function exists at that point. That's all it's saying. A function is differentiable at a point if it has a derivative at that point. A function is differentiable over an open interval. We're going to focus on over an interval if the instantaneous rate of change, aka the derivative of that function, exists for every point whose input is in that interval. So as an example of that, the graph directly above has no corners. It has no points where the tangent line is vertical. So this function is not only differentiable at every point between A and B, but we'll call this function f. F is differentiable on AB, and that is the interval, i.e. the interval from A to B. And that's what it means. It means to say that the function is differentiable at every point between A and B. Okay, so here's an example of a function that has a discontinuity at t equal 9. Figure 2.34 shows the population of Indiana by official census from 1950 through 2000. So as you can see, on the vertical axis, we have f of t, which is millions of people, and on the horizontal axis, we have t decades since 1900, so starting at about 1950 and going up to about 2000. So you can see that the first part of this function from 1950 through 1990 it is a quadratic relationship, and the second part is linear for the last 10 years of it. Can a tangent line be drawn at the point where the function is not continuous? And that is a definite no. That is, we just don't have tangent lines or instantaneous rates of change or derivatives at points of discontinuity. Is there an instantaneous rate of change in the population of Indiana in 1990? And can the instantaneous rate of change be determined using the model F at t equal 9? Explain how the rate of change could be determined. Well, we can't use the model because it has a discontinuity. But in reality, it's just a model. The population didn't all of a sudden in 1990 jump from what it was to what it was going to be. So there's really no discontinuity there, and there would technically not be a sharp curve there. So in reality, we should be able to find that. We would just need a better model. Now, how could we find it in 1990? Well, what we could do is we could say, well, we'll estimate it by finding the slope at a point near it, and that becomes a bit of an issue because we have two distinctly different slopes on either side of 1990, one that's negative and one that's positive. Here's what the publishers suggest. In part B, it says, if it is necessary to determine the instantaneous rate of change, the point of discontinuity, it would be advisable either to use a secant line estimate, an average rate of change, so again, that would be an estimate, or if possible, remodel the data with a function that would be continuous and differentiable at this point. So using their secant line approach, what we could do is we could say, all right, let's take this point here and 1990, and let's pick a point the other side of it, and we could go either side, and let's say we go this way, and as we move closer, you're going to see that the slope is going to get steeper, so more like the function after 1990. All right, that's it for this video.